Apparently we're going live.
Almost.
We're live.
So I'll let you start, you're used to that.
Okay. Alright, so welcome to the live stream for MATH1131 Term 3 2019. So we're going to be working over the Term 1 paper. So I should introduce myself. I'm Joshua Capel and this is...
I'm Laure Helme-Guizon.
Yes. So I believe, Laure, you were lecturing this term?
I was lecturing 1131 last term.
Last term? Okay.
Not this term.
Okay. Alright, so we're not going to... the Term 2 paper, you might have noticed Jonathan already put up some solutions on Moodle, and you really should take a look at them. He worked very hard on those solutions, and I think they're very good. But in the interest of time, rather than trying to write up more solutions for Term 1, we're actually going to do them live.
Yes, and so at the same time we can give like indication of where the idea comes from, what are the common mistakes, and a little bit of advice, not just model solutions, not just the final product.
Of course, that means that we're going to spend a lot more time talking about the problem than we would be writing in an exam. So we're going to be we won't do every problem in the exam. We'll do as many as we can. Now, I guess just a few pieces of advice. You may or may not have heard this advice before, but the exam is 2 hours long, and you have 3 sets of questions. They're just like they call it 3 questions. That means you should plan to spend about 40 minutes on each set of questions. So a good strategy some people have is when you do walk into the exam, so whatever time your exam starts, write down if it starts at 1:40, you're moving off question 1 onto question 2. I think you really should take the chance to try every question. If you just perfect all the questions in the question 1 booklet, well, you've missed a lot of opportunities to
Yes, and at most you get 1/3 of the marks.
Yes.
And maybe if you're stuck on something and spend too much time, later on you will realize that you would have been really good at doing, I don't know, the first few parts of question 3 and you never even touched them.
Yes, and sometimes just leaving and coming back to a problem is also a good idea. Okay, so I think that should have caught up by now.
Okay, do we have some requests, or do we just...
I think we'll go for the problems that we think are good. If there are any requests, maybe they'll pop up in the chat.
Yeah, so as you notice, there is a chat, so you can ask question live, and then we will answer. So you start at 04. I'll put it on.
Okay. Okay, so the first question is about an improper integral, and we'd like to show that the improper integral, well, it says show that it converges. So you know what the result is, you need to actually make sure that the proof is a good proof. Now, the most obvious comparison I can make, so to start with, I guess there's a few things. Maybe let's just have a little bit of rough work in our head. So looking at large values of x, I'm thinking, and this is just rough work, that x cubed over 1 plus x to the 8, well, the dominant term in the bottom is the x to the power of 8. So this, for large x, is going to behave like x cubed over x to the 8, which is 1 over x to the power of 5. And I know what the behavior of this is if I try to integrate. If I try to integrate from 1 to infinity, this is a p integral with p equals 5. That means it's going to be a convergent p integral. So I suspect that this should also, my feeling is this will also be a convergent integral. Now there's a slight issue. If we look at the question, this question integrates from 0 to infinity. And you can't actually integrate 1 over x to the power of 5 from 0 to infinity. So that is going to cause a problem. But actually this comparison can be made a lot more rigorous, because this term here, the 1 plus x to the power of 8, well, that's obviously 1 plus x to the power of 8. So since 1 plus x to the power of 8 is clearly greater than x to the power of 8, you do have that 1 over 1 plus x to the power of 8 is going to be greater than, less than. So actually I can make this comparison quite rigorous. I can actually say that this is going to be less than that. Okay. Now, firstly, we need to take care of that issue. So this was all just rough work. This is not really rough work. I might want to bring that up actually. But firstly, let's just get rid of that 0. So firstly, the integral can be written as, well, it's called I in the question, so I'm going to call it I as well. It was called I think. Oh no, it wasn't actually.
No, but you can call it I.
Yeah, so I might give it a name just in case I'm referring to it again, but I'll just copy it down. So this integral, oh, and I forgot the cubed. Well, I need to split off just the first little part, and it makes the most sense, I think, to split from 0 to 1. It could be anything but 1 that will make it look the most like the p integrals we see. So if you split off the first part from 0 to 1.
You can move a little bit to the side as you're writing so they can see what magic occurred.
Yeah, so we're splitting off from 0 to 1, and I want to then add on the missing piece, which is from 1 off to infinity. So integrating from 1 to infinity, the same thing. Alright, so this actually doesn't cause any problem because this is a nice continuous expression for over all the reals. So this can just be integrated, it will be well defined, it's just going to be a number, and this is the one that's going to cause us the issue. So I guess it might be worth mentioning that this is going to be well defined, so I might just quickly mention that.
Yeah, so the first one is not an improper integral, so you don't need to talk about any convergence, that's just a number.
So how do I want to explain this? So I might just say, because the expression, well, I'll just say it's well defined. So like Laure says, it's not an improper integral. There's no problem here.
So of course improper is when either you have an infinity in one of the endpoints, or maybe your function is not defined at one of the endpoints, which was the problem we had with 0 if we just put 1 on x to the 5th. Is it definite integral when, as opposed to improper? That's the so what I've seen,
it is a definite integral.
I thought it meant as opposed to improper.
Yeah.
I mean,
in this case, I'm just trying to say something along the lines of,
yes,
it's not the problem. This is fine. It doesn't cause any issues. We really want to now understand what's going on with the convergence of this thing. Now, I might be, in the interest of time, I'm going to be very terse here and just say that this will be, well, I've made this observation, and I can probably just use that straight away. So, now I don't like this word, but sometimes I do use it, clearly. But clearly, we're looking at the integral from 1 to infinity of x to the power of 3 over 1 plus x to the power of 8 dx. Well, this term is less, well, it's going to be less than this integral, this improper integral. Now clearly it's a dangerous word because it has to be clear to you for you to say this. If it's not clear to you, it won't be clear to the person who's reading, I think.
Yes, and sometimes we see clearly as a way of saying, I'm not really sure what happens here, but I'm sure it's true, let's move on.
Yes.
But the person marking the question usually picks this up and could be a little annoyed.
Yes, so if I want to make my solution better, I should actually bring up this black explicitly. Here I'm being lazy because I sort of wrote it in my rough work and saying that clearly this is true. I checked somewhere else. We have that is equal to that, and this is a p integral. It's p equals 5. So since 5 is greater than 1, that's a convergent integral. So by comparison, this is also convergent.
Don't we usually write the comparison first? We compare the function and only then do we put the integrals around them?
No, I'm happy with this personally. With this? I like doing it this way. I mean, there is a slight issue because if one of these is not defined, you're writing down, this should be a number.
Yes.
If this is not convergent, then this is just not really a well-defined object. But in this case,
in the end it is. But you didn't know until you got there.
Well, I knew it was going to be
Yes.
from before. So
Yes.
yeah, there is a text. Yeah, well, I don't want to dwell too much on that. I think this statement is fine. Other people might want to talk about this first and then chuck the thing around it.
Do you want to write something about the p-test or p-integral or something?
Yeah.
So that the
So we have
word is
clearly
somewhere?
this is true.
Yeah.
And because so by so we are comparing it to a p integral.
You wrote integral funny.
Oh yes, there's no.
Yeah.
Sorry. With p equals 5, specifically p is strictly greater than 1, that's the important part. So by comparison to this p integral, we have, well, by comparison to this, the improper integral, I'll just write it down again, so this one we're looking at is also convergent. So there's two things that happened here. This is the comparison, so it's really the comparison test, I think you've got them. It is by comparison, and we have to bring up, we are comparing it to something we already know. These are simple integrals which we already know the convergence for. So by comparison that is also convergent. And if I want to be very complete, I wasn't really worried about this integral, it's the combination I wanted. So here's where my name is useful. I will put in the conclusion. Hence, I is a convergent improper integral. But I'll say improper.
Yes. So as Josh said, in your solution you have to make sure that we understand what key ingredients you use. So we need the word comparison somewhere, so we recognize this. And we need either something called a p-test or p-integral, but we know what tools you've been using. And these are the two main ingredients, so you need those words.
Yes, and I think I'll be forgiving of spelling, considering I tend to get it bad myself. So yeah.
I don't see any question in the chat, so that probably means you have no question about that.
So no questions yet.
No question here, so maybe I'll just put on the next question.
Sure. So no questions?
No. Okay, the p-integral, it's when you integrate, let me pick a pen there. You can clean here, so I can write here. There's a theorem that says that if your integral, and here it's infinity and here it's 1 or 2 or whatever you like, and if your index here or your exponent is p, then there's a rule that says if p is greater than 1, then the integral converges. I'll call this I sub p. I could even put an equivalent. And in all the other cases, your integral diverges to infinity. You need to know this one, it's so useful. Because not only you need to be able to use the theorem when it's in front of you, but see what Josh did. He saw an integral, and because he knew that comparing to those functions would enable him to use this theorem, that pointed him to, let me try to see if my function is bigger or smaller than the well-known integrals. You need to know that.
Yeah,
And thanks for asking the question.
Actually, I did have a question about this. So you lectured calculus last time, is that right?
Yes.
So did you ever call some people I think have called this the p-integral test. Have you called it the p-integral test?
For me, the p-integral is the integral itself. And then the test is, let's compare, let's check if p is greater than 1 or smaller or less than or equal to 1. That's the test, that's the integral.
Because I always thought of the p integral test as, is it a p integral? Then yes, I know the answer.
No, I think what they really mean is that.
So that's why I try to avoid the word p integral test. Personally.
Okay, so we have another question, which if p is equal to 5, why would it be improper? So improper just means that there's a problem. The problem could be there's an infinity. So no matter what I put here, this will be called improper, right? And now, so that's one way of being improper. Another possibility, let's say here I have a 1, and my function is not defined for x equal to 1. This one would be improper also. And now every time if it's improper, basically there's a problem, two things can happen. It converges or it doesn't, right? So the word improper is different from the word convergent. It just means there's a problem, so we're trying to solve the problem by using all the tests we have.
Yeah, so we managed to avoid this particular problem because it wasn't improper at that point, but you had to be careful not to make it improper.
Yes, exactly.
So yeah, we can't. This can't be integrated from 0. It has to integrate from something non-zero.
And as you remember, if there are two problems, and lucky you, then you need to break this into put whatever you like here. So you have only one problem each time, and it's going to be called convergent if both of them are convergent, and you may need to use all the rules and tests you have.
Okay.
Any other question on this one?
I think maybe we should.
And I just messed up the board, you had just
No, that's
cleaned.
okay. As long as it's not too much mess, it's easy to clean, I think.
So while it's erasing, if you haven't done it, think carefully about the question up there. You will get much more from seeing the answer to a question you've thought about than just, watching us do it. Okay, so the question tells you that you have a function which is differentiable. You know the value of the function. So maybe I'm going to write it just for myself. Maybe I'll take the question for me. So we know the value of the function. We know the derivative. And we want to find the value of the function really close to 2. So first, of course, we don't have a formula for the function, otherwise we would just sub in and that would be the end of the story. You actually get some help. They tell you find the tangent line and use it to find an approximation. So if you want to get an intuition of what's happening, you have your function. And then, so of course I'm making up the drawing because I don't have the formula. That's x equal to 2. And then let me put a little bit of color. And at that point, I can draw the tangent line. And I'm going to zoom a lot because I want you to see something. Do we have color? So let's say 2.01 is here. The value I want is the y coordinate of that point up there. So really this point has coordinates 2.01 and f of 2.01. So I want the y coordinate. Unfortunately, I can't get it. So my best guess for what it would be is this value on the tangent line. And that's what's called the tangential approximation. So let's do this. So as you know, the equation of the tangent line, so let me write this. Step 1, the equation of...
We should try to avoid green. It doesn't show up on camera very well.
Yes, green is terrible indeed. The equation of the tangent line at x equal to 2.
This is even worse.
I brought some, maybe those big blue ones. So your equation is y is equal to f dash of a times x minus a plus f of a. You don't need to reprove this every time, you know it. Your f dash is given, it's a 3 times x minus 2 plus 1. So the equation of your tangent line is y is equal to 3x minus 6 plus 1 minus 5. So they were asking for the equation of the tangent line. Really, I think we could have gone faster because really we're going to be reusing it. But the idea is if I want to calculate the y coordinate of that point up there on the curve, it's almost the same. It's going to be almost the same as what I get if I'm on the tangent line. If I'm on the tangent line, what I get is f of 2 plus f dash of 2 times 2.01 minus 2. And so I'm going to get f of 2, so I just look over there, that's a 1 plus 3 times 0.01, and that's equal to 1.03. Right? So that's an approximately equal to, because the point I wanted is this one, and I'm taking this one, and that's a real equal, because here I'm on the tangent line. So this, I keep going on the tangent line. And we get this value.
Okay.
Question on this one?
I don't have any questions. I do have my own comment though. So, personally, I kind of prefer this form, to be honest. The simplification, it does look nicer, but I really like this because, especially what happened down here when Laure put in 2.01. This number here is a sort of a difference from the point you're looking at and 2.
Yeah.
So it is a really nice way to formulate it. You sort of formulate it in these little differences. And I guess I'm only saying this because you will be back here in MATH1131 in the future, and we're going to see a superpower version of this.
Yes.
But for now, we're just doing this tangent line one, and I kind of like that.
And indeed, yes, so you're right, that's exactly what I did in the end. I used a non-simplified form. It's approximately equal to what happens at the function, and then you have this like correcting term that says you're slightly away. So that's exactly what I did.
So there is one question.
Purple doesn't work.
I think
It looks like black.
No, purple I think is better. It's very visible. The green and the blues I think are washing out.
Yeah. There's a question, but I can't read it. It's too far
the question
away.
is asking essentially how do we get this? How do we get this tangent line approximation? Can we explain more on that? I do have a way to remember it if you're really struggling. So should I write that down? Maybe black. So one way.
Erase that.
Yeah, one way I remember this is to remember.
There it is.
Well, the way I'm going to remember it is to look at how we define the derivative, because this is kind of one way to think about this tangent line approximation, and it's not the only way to think about it. But one way to think about it is you have your value y minus f of, not x, it is a. So whatever point we're looking at, f of a.
Take the big black. It's more readable.
Thanks. So I'm looking at y minus f of a. So this is the sort of, if you think about it, it's this value here, the y value minus, it's this y value minus f of a over x minus a. Now as a gets closer and closer to x, what you're going to get is an approximation for the derivative. So you can think of this as saying that this is approximately the derivative at a. So this quotient, so it's the rise, so the change in y divided by the change in x is approximately f prime, the derivative at a. And if you just rearrange this, you'll get y minus f of a is approximately the derivative at a times x minus a. And a little bit more rearrangement just moves the f of a to the other side. That will give you Laure's formula.
Yes, or that one. Yeah.
So this is a nice way to remember it. It is a nice way to remember it for one variable functions. In the future, you might actually find this might be harmful, this way of thinking about it, but for now, it's a nice way to think about it. Right.
Okay, so next one. The geometry one?
This is...
Or do you want to do the one with the ln and the cos? We were wondering about that one.
Yes, we can show it. Maybe just a quick discussion.
Okay. Sorry.
So here, we're looking at an integral, and it says we need to make an appropriate substitution. Now, really, I think this question is just, have you practiced your substitutions enough? Because it should be fairly obvious when you look at this problem what you need to do. At least if you've had enough practice, it should be obvious. So what's very nice about this problem, where did I put the drying cloth?
There, maybe?
I'll borrow this one.
This one's dry.
This must work.
It looks like a class on housekeeping.
Yes. These boards are hard to keep clean. Alright, so if you're looking at this problem, so what you should think about is, well, I mean, the first thing that jumps out to me is there are log x's everywhere, and there's one thing I know about log x which is very, very helpful here. So
These few seconds are for you to try to get the hint. What does he have in mind? Something should jump to your eyes.
So let us set, and what jumps out is, I think, it looks to me like u equal to the log of x is a good substitution, and that's not just because I see it everywhere in the formula. The reason I think it's a good substitution is because of the consequence. So what this gives us is that dx is going to be du, thank you. Yep. It's always good to spot when you're about to make your own mistakes. I'll skip that entirely. So it's going to give us that du is equal to, look at that, du is equal to 1 over x dx.
And that's half of the reason you should have thought of the substitution. You see a natural log and you see a 1 on x, so its derivative is there.
Yeah, so it looks like this is going to be perfect. And I won't do too much of this problem because I think the rest should just be fairly easy calculation. This gives, well, this integral does have a name, I, so I will call it that. It's the integral. Well, the log of x is just u. The cosine of the log of x is just the cosine of u. And 1 over x dx, that is going to be du. Now that's nice because this is an easier problem to solve, but it's actually testing us on two things, because to do this we need one more technique. And the technique is integration by parts. Now, well, that's not too hard to do, so I guess I might as well do this.
Yes, and I've seen some students wonder, which one should I differentiate? Really what gets in the way is this u on the outside. If you had only cosine u or sine u, that would be easy. So if you want the u to be gone, you differentiate it and you're going to be getting a 1, so that will solve your problem. Just try to foresee what's going to happen. If I differentiate this one and integrate that one, what happens? And see if it looks better or worse.
Now, so our goal is we want to differentiate that one. Now the way the integration by parts works, you need a derivative to begin with. So I'm going to rewrite the cosine, because I know the cosine is the derivative of a well-known function. It's going to be u times, and I do need to be careful because I often make mistakes here. I know it's either plus or minus the sine. Let me write down sine to begin with and then check that works. So derivative of sine, yes, that's cosine. Now this is just the way I do integration. I look at it, well, I can never really do it one way. I have to do it reverse. I can do derivatives very easily, the opposite way not so much.
And you're probably going to make a lot of mistakes if you try to memorize the formula for integrals. I do exactly the same. I know it's plus or minus and I differentiate. So I know two formulas, derivative of sine, derivative of cosine, and I don't get them mixed up with other formulas.
Yeah, it's essentially just turn the problem into a problem you know you can solve.
Yes.
So I can't do the integral, but I can do derivatives. Now, the integration by parts formula says you do the product without the derivative there. So that's u times the sine of u. And then you have minus, and it's the product where you swap the derivative over. So this is du, or a funny way of writing 1 times the sine of u. Du, well, we're very close, so I might as well just finish it.
Yes, and from the beginning, you knew that you wanted to differentiate for that reason. Differentiate the u.
I mean, that was the goal. So minus the integral, well, I'll just say that is 1.
It's 1.
So the integral of sine, and again, I'm not very bright, so it's cosine plus or minus cosine. Let's just double check. Derivative of cosine is actually minus sine, so this doesn't work. I did a minus sign. And all over up to a constant. Oh, not quite done. So the last thing to do is u was something we introduced, but we need to go back to x. So log of x times the sine of the log of x plus the cosine of the log of x, all up to a constant, full stop. Yeah, I mean, it took a lot longer to talk about the problem than actually do it, I think.
Yes, and with the usual warning, the question was about x. It was your idea to introduce u. Fine if it helped you. The question was in terms of x. You need the x. And there will always be the person who forget the constant. But when you have this integral with no endpoints, what it means is, please give me all the antiderivative for that function. So you need plus c. Otherwise, you're missing some of them.
Okay.
Okay, so I'll put on the next one.
No questions yet.
If you have a question, it's a good time. You probably can't hear me when I'm there. No. I think it was 7.
Should be.
So maybe it's 8? It's 8.
8, yes.
Yes.
You'll have to hide 7, it's still visible.
Mm. Okay, so this question takes a lot of space on the board, so maybe at some point we'll take it off. So you have a geometry question where you have 3 points, so maybe I like to store the coordinates of my points somewhere. It's going to help me do the calculations. 2, 0, and -3. B as coordinates 0, 2, and 1. C as coordinates 4, 2, and 5. So I'm told that we are working with the triangle ABC. So we are in 3D, but ABC is made of 3 points. 3 points define a plane. So what I'm going to do is try to visualize what happens by putting the 3 points in a plane. One of the messages about this one is don't even try to do anything to scale using the coordinates. You want a plane, you get a plane. So I will have a plane maybe like that. In this plate, I put A, B, and C, and as you can see, more or less randomly, and that defines my triangle. Okay, these 3 points are in a plane because any 3 points are always in a plane, right? Okay, so X is the midpoint of BC. So X is the midpoint of BC, which is, I can write it like that on my drawing. So my first question is, find the coordinates of the vector AX. So for that I need the coordinates of X, which we can get in a lot of ways. I like to have all my points in the same place. You can use your year 10 method, which basically tells you if it's the midpoint of BC, just average the coordinates. So that's going to, like x1 plus x2 over 2, so that's a 2, which is why I like to line down. Average of 2 and 2 is 2, and the average of 1 and 5 is 3. So I get my x, and now if I want the coordinates of vector AX, as you know, we take the coordinates of the terminal point, 2, 2, 3, minus the coordinates of the initial one, minus 0, minus 3, which is plus 3, and I get 0, 2, 6. That's question A. Done, I would say, in the year 10 way. You wanted to do it differently, Josh, right?
Yeah, it's not the way I thought of when I did it.
I mean, there are different. So what we could do if we want to look like we grew up and we got good at vectors, we could say AX, and what you know is something about BX. So what you could do is use this tip-to-tail addition rule that says that if this vector ends with B and this one restarts with B, this addition works. Be careful, it only works with vector. It doesn't work with distances. So we could calculate the coordinates of this one. And then BX is going to be half of BC, because that's the definition of the midpoint. Then from all the coordinates you have over there, you can easily sub in to calculate the coordinates of these vectors, and you will be getting the same result. Right? So I'm not doing this. Next question. we want the equation of a line, the line that goes through A and X. So it's this line. So as you can see, I'm going to keep adding things on my drawing as we go. And I would say, maybe if that's the only thing you remember from this exercise, have a drawing and try to visualize what goes on. I won't have lost my time. So we want the equation of this line. And what we know about the equation of a line, they always look like, so that's the coordinates of some point, an arbitrary point on the line. Here you need to choose one point on the line. We could choose A or X. Probably it's safer to choose A in case I made a mistake in X, but you could really choose X if you want to. And then plus lambda, some vector which gives the direction of the line. So the most intuitive one to pick is A sub X, but I can see that if I divide every coordinate by 2, I'm just going to get smaller numbers. And because L1 reappears later on in the questions, maybe I will be better off with smaller numbers. So what I'm going to do is divide those by 2, because if I divide those by 2, I get a vector parallel to AX, so it also gives the direction of the line. So 0, 1, 3, and lambda can take every value over R. And for each value of lambda, you get 1 point on the line. I could say as my vector 0, 1, 3, which is 1/2 of A sub X, gives the direction of the line. Okay, so we have this equation. Oh, there are plenty of, there are questions on the chat, right?
This was a question about the last question. I might do at the end.
Okay. Because I'm at a distance, I can't really read. Then we are given the equation of another line, which I'm going to write because I like to have everything in the same place. So there is another line, and it's called L2, and it's the median through the point B. So we are reminded what the median is. I'm going to try blue, maybe this big blue. So the median through B has to go through B, sure, and it has to go through the midpoint of this side. So let's say, so these two things are equal, and that's my line, L2. And the idea is, if you could do one, you would probably be able to do the other one, so we're not asking you the same question twice. So this time it's given to you, 0, 2, 1, which C goes through B, and then the direction of that, one vector which gives the direction of the line has been calculated for you, and we get 3, -1, and 0. So show that the two medians intersect at a point. So they're giving you the point which is the center of gravity, if you remember correctly, hence the name, 2, 4/3, and 1. You have some options here. They gave you the solution. So if you want to, you can just check it works, right? So method 1, check that this point, G, is on both lines. And so really you look at that and you say, is it possible to get G? G is given to you. Can I get a 2, a 4/3, and a 1? Provided I choose the correct value for lambda. And if you stare at this for 1 second, the second row is really promising. The second row really is lambda. So that tells you lambda must be 4/3, and then you can check that lambda is equal to 4/3 works for all the others. So if you're not convinced, you can calculate -3 plus 4/3 of 3. That gives you, that's going to give you a 4, and 4 minus 3 is 1, right? Then you can do the same thing for the other one. So that happens when so we can say G is on the line L1, and you can do the exact same thing for the other one. Do I need to write out the details, or do I just give the value that works? What do you think?
I think just give the value. Yeah.
Yes, and then, so really you write the same thing, and you get for mu, so what did I pick for mu? is for mu equal to 2/3, G is on the second line. So if it's on both lines, so the question was prove that it's the point of intersection of these two lines, and you just proved it's on both lines. Just a word of caution, if you did this exercise previously and maybe you didn't really have a problem keeping the 2 and the 6 and you didn't divide by 2 like I did, then the value of lambda you will get will be different, but we could really both be right. So don't worry about that. So that's method 1. Method 1 only works in cases where you have been given the solution. So maybe you should also be able to do the general case when they ask you, do the lines intersect? So there's nothing to check, you really need to solve. So I need some space. I'm going to do a little bit of cleanup. I'd like to keep the equation. Maybe I can take off the question, because I copied whatever was important in the question. Yes, let's just take off the question entirely.
Do you want to keep the last, this part, I guess, do you need?
Yeah, maybe, yes. And let's remove, so I can write up to... Okay, here works. So if I want to solve, so method 2, I want to find the point of intersection just by solving. So that means this point, so this really says this point is on the line, and this says this point is on the line. I want it to be on both. So I'm going to say 2, 0, minus 3 plus lambda times 0, 1, 3 is equal to 0 to 1 plus mu times 3 minus 1, 0. And I want to rearrange this. So I'm going to put the lambdas and the mu's on the left. And when I move this to the left, I really have two options. I could either put a minus in front of the mu and keep these coordinates, or I could put a plus in front of the mu and change the coordinates. And the thing is, because I have an eye on the future, and I know how we're going to solve, you know, when you have your system of equation, you need a plus. So I'm going to put a plus there, and I'm going to put a minus 3, 1, 0. If you'd like, you can write this, if that's more intuitive to you, and then you can distribute the negative sign, and you're going to get there. As you can see, I'm trying to save a little bit of board space. So I move this one to the right. I'm going to get 0 minus 2. That's minus 2. Then 2 minus 0 is a 2. And 1 minus minus 3. So 1 plus 3 is a 4. And now I'm sure you've recognized the perfect setting to put all of this in an augmented matrix. So I put that in my augmented matrix. That's the column that corresponds to lambda. You don't have to write it. I just like to remind myself what my variables are. 1, 0. And then here I put the right-hand side. Okay, unfortunately, I have a 0 there. So what I'm going to do is just swap the first two rows. So sorry. I'm standing in front of what I'm writing. This doesn't work too well. So I'm going to swap the first two rows, and I'm going to get 1, 1, 2, 0, minus 3, minus 2, 3, 0, 4. So I'm going to use this as the pivot, and I'm trying to get a 0 where the 3 is. So what I'm going to do, I'm going to keep the last row. So my code for keep is multiply by 1, so it means do nothing. I'm going to multiply this one by negative 3 and add. What do I erase? I'm going to erase this. I want to keep my drawing.
So screenshotted your drawing, so I can bring it back if you accidentally erase it.
Yes, you're right. If we don't draw, it doesn't really work. So the row operation I'm doing here, I'm calculating row 3 minus 3 times row 1, and I put the result into row 3, which we write this way in computer science, for instance, and in math also. So all the beginning is unchanged. The first two rows are not affected by that. And what I get for the last one, So maybe look at if you've never done it this way, if not really good at mental math, just watching the fingers will probably help. You have 1 times 3 and minus 3 times 1. So really minus 3 plus 3, that's a 0, that's why you picked that. Then that's a minus 3 plus 0. And then you're going to get minus 6. What have I done?
So you had 0
minus
3.
6 plus 4. This is not
So
working.
the second entry in the bottom row should be minus 3, shouldn't it? 0 minus 3 times 1.
So where?
You're looking at the bottom.
This one?
So I think because you said you were taking this row minus 3 lots at the top row?
Yes.
So 0 minus 3?
Oh yeah, 0 minus 3. Okay, yeah, that's better. Yes. 0 minus 3. I was thinking, what is wrong here? And so minus 6 plus 4 is minus 2. Ah, that looks better. So one last step, as you can see, what I'm going to do, I'm going to subtract, and I'm going to get 1, 1, 2. Do I still need the lines? I'm not sure I still need the equations of the line, right? What do we do next? Find some distances. No, we don't really need the equations of the line, so they're gone. So here I'm going to get 0, minus 3, minus 2, and then that. So because the right-hand column is not leading, we know there's a solution, and really you can rewrite this as an equation. So my first column was lambda, my second one was mu. So this equation is really minus 3 mu is equal to minus 2. So mu is equal to 2/3. And then we can sub this in the first equation, which really means lambda plus mu is equal to 2. So lambda is going to be equal to 2 minus 2/3, and you're going to get the 4/3. So this method is much longer, but it can do more for you, because if you're not given the point of intersection, then you can find it, right? And then you will get plenty of questions where they ask, what's the point of intersection?
Yeah, so I guess I do think, I mean, you can sort of even just see from the length. Laure's first method was very good for this problem. We gave you the point, we were saying, it really is just asking, can you find the value, which gives you the intersection. This would be a good question for maybe testing your row reduction abilities and your solving linear equation abilities, but they didn't really want to test that in this question, so they were sort of, I think they were giving you the point, so you didn't necessarily have to do this.
Yeah. Now we're thinking maybe some people have done it and now they want to see how it's done. And according to my philosophy, everything we learn goes on the picture. That's the point of intersection. That's what we just did. So we get to question D, and something new happens. We get a new point, which is called D, and which is not on ABC. So find a Cartesian equation of the plane pi, which goes through D and is parallel to this one. So there's another plane parallel to the previous one. There's a point D in this plane for which we have the coordinates. So I'll add it there with all my other points. And we want the Cartesian equation of that thing. So what we know is, if we had a normal vector for this plane, everything would be good. So this plane is called pi. So if we could just find a normal vector, that would be the end of the story. And we know that two planes are parallel. So what we could do is, if we can find a normal vector for that plane, if the planes are parallel, the same vector will work. So I just need to find one. So let's find a normal vector for the plane going through ABC. So if I do, so what I can do, of course, when you want a vector normal to two other vectors, the cross product jumps to your mind, I'm sure. So what we could do is AB cross AC and find a normal vector this way. Let's calculate AB. So, and 0.0, sorry. If I say 0 and I write 2, it's probably not going to work. Coordinates of B, so 0 to 1, minus 2 minus 0 plus 3. So that's minus 2, 2, and 4. Then I need AC. Okay, I picked AB and AC. If you want to build your normal vector using, I don't know, CA and CB or BA and BC, whatever. Sometimes some points have easy coordinates and others are fractions, so you just choose what's easy. It's mathematically equivalent, but not necessarily equivalent in terms of difficulty of computation. And again, that's the case. So I want to calculate the cross product of these two vectors. I'm only interested in the direction of the result, not the magnitude. So what I'm going to do, I'm going to divide all the coordinates by 2 each time, so I can work with smaller numbers. And that's one of, there are really 2 things I wanted to show you from this exercise. The first one being have a drawing where you can visualize what's going on. If you don't have the drawing, I'm not sure you will realize that the tool we need is a vector normal to both planes. And really, sometimes if you're only interested in the direction, you can simplify things. So what I'm going to say, 1/2 of AB cross 1/2 of AC is normal to the plane. I'm going to give it a name. I'm going to call it N. Is normal to the plane through A, B, and C. And I'm going to calculate it. So when we calculate the cross product, we know that here we have the basis vectors. And then so I'm going to take these vectors. Some lecturers write the vectors horizontally. I write them vertically. The vectors are written vertically everywhere else. We get the same result. There's no special reason to make them horizontal. And I just said I would divide all the coordinates by 2. So I get -1, 1, 2. And then my second vector is half of BC, which has coordinates 1, 1, 4. And from there I calculate. So if I cross those two, I cross the I, so I tells me it's the first coordinate, and I'm left with 4 minus 2. Maybe some of you think of this as the gamma rule. I don't know how. So 1 times 4 minus 2 times 1. So I guess 4 minus 2, that's 2. Now I'm going to erase my gamma because I'm going to calculate another one. As you may remember, the difficulty when you calculate determinants is the signs alternate, so plus, minus, and if we had more, it would keep going. So I'm afraid of forgetting this, so the first thing I do is put this minus sign. Now I cross those, and with the gamma rule again, I get -4 minus 2, so that's -6. And I cross k, because I'm crossing k, I know it's going to be the third coordinate, and I get -1, -1, so that's -2. So I got a vector which is normal to the plane. And again, all my coordinates are multiples of 2. So I'm going to say that n1, I'm going to use this one, half of n, with coordinates 1, 3, and -1, is normal, well, to both planes, so in particular to pi. So I'm going to add an n1, because after all, the one I'm going to use is n1. And I will be erasing this.
While Laure's erasing, I might just point out, I worked with this expression myself on paper as well. I was trying to be lazy and not make these numbers nicer to work with, and I made a lot of mistakes. So it isn't a nice idea to actually, if you can get a simpler object which does the same job, maybe work with that instead. So n1 here it's much nicer to work with in the end.
And I've already divided by 2 3 times. So if you didn't, you have some 8s everywhere. Everything's going to be a multiple of 8. Okay, equation. So we don't forget we're after the equation of this plane up there, for which we know a point, and now we know a normal vector. It's there. Let me just see. Yeah, so I can write from here. So let's write the equation of the plane. A point in the, well, there are two kind of points in the plane. Those which are on this plane and those which are not. I'm sure you believe me. A point is on the plane if and only if. And again, that's very visual. If my point is on the plane, then, oh, I'm on camera. Then one point, so that's D. If a point is on the plane, then the angle between dp and the normal vector will be 90 degrees. So I can say, if and only if dp makes a right angle with the normal vector, which is the same as saying that vector dp dot n1 is 0. And that's going to give us the equation in no time. P has coordinates x, y, z. So as usual, coordinates of a vector is terminal point minus initial point. D is written over there, -1, -2, -3. N1 is there. 1, 3, -1 equal to 0. And when you expand, you know what the result should look like. Try to do get all the terms with letter at once and then put all the constant later. So I get 1 times x plus 3 times y minus z. And then let's go pick the constants. I get a -1, I get a -6, and I get a +3 equal to 0. So the equation of my plane is x plus 3y minus z, and I'm going to -7 plus 3, so that's a -4 equal to 0. I remember +4 when I did the calculation. Let's try, let me put D in there. D as coordinates 1, 2, 3. So I'm getting 1 plus 6, that's 7, minus 3 is 4 minus 4. Okay, so it's just my memory. That works. And of course, as you know, you can check the normal vector directly from the equation of the plane. It will be 1, 3, -1, as should be. And that's a Cartesian equation. So finally, last question. We're getting there. We want to find the distance between A and pi. So we want this distance. If we go vertically, at some point we're going to hit. So what we want is this distance. So maybe I can just redraw the interesting part, because we're starting to have lots of things up there. So I have A there. Here I have my, what I want is the distance to the plane, and I have a point D in the plane. And the direction of this is given by my normal vector, right? So it should be pretty clear to you that if I take the vector AD and I project it on N1, what I'm going to get is that vector. So and then the question was the distance, and the distance will just be the magnitude of the vector. So the distance between A and the plane, is that a notation allowed in, do we use this? Okay, words. Not sure.
I can understand it, but...
Yes, because I'm saying it at the same time, so I'll just... so the distance between point A and the plane, pi, is the magnitude of the projection, and I'm projecting AD onto N1. And then you know the formula for the projection, you just do the dot product of these two vectors, and then you divide by. I really should have swapped the names and called N1 N, because now I have all these N1s everywhere. And I need to put some absolute values. Yes, so in that case, what am I, no, that's not working. I forgot an N1, because that's a number, and the projection should be a vector. Right? What have I done here?
So you're missing an N1?
I'm missing an N1. And that's the reason why I was saying absolute value. So that's an N1. I'm going to call it N because I think that all these ones look like dots. I'm afraid people will be confused. What do you think? Or I write better ones?
So it would be true for n as well, but more.
It would be true for n as well, but I don't want that in my calculation. Let's calculate. Okay, I need a little bit of space to calculate this dot product. And I don't need this anymore. So do I have AD somewhere? No. That's why I usually like to keep track of all my stuff in some corner, but I didn't do this time. Because I keep erasing. So I'm getting -1, 2, and 6, sorry. Therefore, if I do AD dot N1, what I'm going to get is -1, 2, 6. N1 is hopefully still there. 1, 3, -1. And so we're going to get -1 plus 6 minus 6. Okay, so I can put this back in there. So maybe here it would be smarter to notice that that's the square of the magnitude and that's the magnitude. So I get the magnitude once, right? So let me rewrite this first. So at the top I have a number. This dot product is a number. And then we know that if you calculate the dot product of a vector with itself, what you get is the square of the magnitude. So I'm going to have the square of the magnitude here and the magnitude there. So at the bottom I just get the magnitude of that vector. And let's sub in. So at the top I get the absolute value of that, absolute value of -1, that's a 1. And if I want the magnitude of n1, I just square the coordinates. I'm going to get a 1 squared plus 3 squared plus -1 squared. And that's going to give me a 1 on square root of 11. And that's my distance. And that's it, finally.
So yes, this question had a lot of concepts being tested in it. Actually, just a curious thought about this while it's here. So I think where Laure was writing down this notation for distance. It reminds me of what happens in programming languages where people want to try and shorten things quite a lot, and then they realize, actually, we don't need short notations. Words do explain things quite as well. So you can always just use words. Of course, words do take longer to write down, so they're cutting into your time. And you will experience this, the difference between these vertical lines. So this is meaning a magnitude because it is around a vector.
Yeah.
And these are absolute values. They're the size of numbers.
Which is why sometimes you see double bars around vectors and simple bars.
Yes, I prefer this notation. If I could change the notes, I would, but that's outside my decision. So I like the double bar notation.
I always use double. I struggle to not use double bar. If you come to my
consultation, I might slip into using double bars.
Yeah, so will I.
But yeah, it's nice to know what is a magnitude and what is an absolute value. And even with the determinant, you see more vertical lines. The question.
So if you hadn't done this exercise before watching the stream, the fact that you watched me do it doesn't prove you can do it. It's like watching someone swim. Maybe you can't swim. So I would really say redo all this calculation. It's really easy to get a lot of things wrong.
Yeah.
And practice is what you need.
Yes. And it was a good thing here that where Laure did get this equation here and thought, ooh, actually I'm not sure if I made that right. Well, it works for every point on the plane, and you know a point on the plane, you know D was on the plane. So it's very quick just to test and say, I'm convinced at least that D is on this plane here.
Yeah, and also use the nature of thing. Initially, I just wrote a number, and I was thinking, it can't be a number, it should be a vector. So that's when I realized I'd forgotten something.
Yeah, so vector here, also still a vector.
Well, since we started, and no one has stopped us, let's put double bars around every vector.
And now the size of this vector can be calculated by the ratio of these two numbers. Anything else I want to say? So actually, there was a comment that came up earlier. I might see what Laure thinks about this. So someone was asking about integration by parts. Can they use something? They call it the ILATE strategy. Have you heard of this?
No, I have no idea.
So the trouble is, it sounds like a sort of a technique people have learned to say, if you see an integration by parts, this is probably the methods you should try.
There's only one way to do integration by parts, right?
I think it's more, you have to choose which one you're going to differentiate. Or you have to but for that, I feel like if you're just learning some algorithm you may not be understanding?
I don't think you should learn some algorithm. You should say, if I differentiate, for example, this x will be gone and I will be left with only sine or cosine. Even if you don't know yet because you didn't calculate.
Yeah.
You see, that's going to be easy to integrate.
If you know what the goal is, then
Yes.
it'll lead you in the right direction.
Mm-hmm.
Plus, I mean, the honest truth is you can use a technique like that, but you wouldn't write that down on paper because nobody has any idea what you're talking about.
Yes.
So you would say, this is my choice. How you got to that choice? Maybe you've learnt an algorithm from some school, but I would just say, you look at the problem and you see what you want to do.
Just like if I had this one, an algorithm is not going to tell me which one to differentiate. But in my head, I just say, maybe if I differentiate this one, here I'm going to get an x, and with things, I don't care for now. And this will still be there. And I will do it once again. If I differentiate, if I keep differentiating this one, I'm going to get to 1. And I'm going to get something I can integrate.
Yeah,
So
we're
I
not
think
worrying about the constants in this discussion. We're just saying, it'll look like this, this is the direction I want to go.
exactly. So that's the way you choose the direction. It's not an algorithm. Try to foresee what's going to happen, what mix of functions you will get in the integral, and is it something for which I can find an antiderivative, yes or no?
Right. So I think we should move on with the next question.
Yeah, we can move on with the next question. I'll take. So you're doing the one with the matrix, right? So I'll put out the one with the matrix. He's not cleaning.
I'm going to go once over it and then over it again to get all the spots I missed. Trying to be an efficient cleaner.
Good
Okay.
time for you to ask questions.
Unfortunately, it looks like there's still a slight delay.
Yes.
So by the time you thought of a question, I would say get the questions in as soon as you think about the question.
Yeah, because you can see sometimes us looking at the screen and there's a delay and we're wondering, things are okay.
All right, so let's see. We have a matrix called R, and we're just going to do 3 things with it. One, it says find the determinant of the matrix. Then we want to find what happens when we multiply the matrix by its transpose. And finally, we have to simplify some expression involving this matrix and some other matrices. Right, so let's start with the first one. Now, you do need to be careful here. I didn't mark this question, but I can see a mistake that I imagine a lot of people would make. There is this half outside the matrix. Now, the question is, how do I want to deal with this? I think I'm actually going to bring it inside the matrix. This is the way I'll do it. Maybe Laure will have a better method, but I will bring the half inside just to make sure I don't make a mistake. So I'm trying to find part A. Just do a calculation. Determinant of R. It is the determinant. Let's bring that half inside. We get a root 3 on 2. We'll get, well, half of 0 is 0. A half of 1 is a half of 1. You get 0, 1, 0.
Yeah, the mistake that Joshua has in mind is people are wondering, if I calculate the determinant of the thing on the right, should I multiply it by 1/2? Should I multiply it by 1/2 to some power? And if everything is inside, you won't have this doubt.
Yeah. So
And once we get the result, we'll try to see actually, there's a rule. So if you don't like fractions, I don't like fractions. There's a way out.
Yeah, so this is me being ultra cautious, but there is another way to do this. Alright, now when you're doing a determinant, you do need to pick which row and which column you're going to expand across, or you have a choice. Now, the first row looks pretty good because there's a 0 in it, so I'm only going to have 2 determinants to calculate. But actually, the middle row looks even better because there's only one non-zero number there. So I can do it by actually just expanding across the... I'm going to expand across the second row. Now, I am going to keep track of this checkerboard pattern of pluses and minuses, or chessboard, whichever you prefer. So it's going to be minus 0 times something, but minus 0 times something is just 0. So So the only non-zero term I get here is a 1, and that corresponds to this plus. So that's really nice. I'm just going to knock out that row, knock out that column, and it is, I'm switching notation unfortunately, root 3 over 2, a half, minus 1 over 2, and root 3 over 2. So some people write det, some people write this, they both mean the same thing. And now there's no way out, I just need to do that gamma rule that Laure mentioned. I hadn't heard the name gamma rule before, but
Oh, okay.
so this times this minus that times that.
Yes.
So it's going to be root 3 times root 3 on 2 times root 3 on 2. That is going to be 3/4. Yep, that's right. Minus, well, it was a minus, but another minus sign from that, so it's going to be minus minus a quarter. Really nicely, this is 3/4 and another quarter, so it's 4/4. It's 1. So that's one way of doing it. You know that the determinant of this matrix is 1. Now, do you want to talk about the other way, or would you like me to?
I can do that.
Okay.
So another possible way is to think that if you have, so just in general, if you have a matrix and you multiply it by lambda, really you're going to be multiplying every row by lambda and every column by lambda. So when you calculate the determinant, what you will get is a lambda to the power of n being the number of columns or the number of rows. See, for example, here each row has been multiplied by 2, so really if you compare the two determinants, for the other one you're going to get an 8, and that's your 2 to the third.
Yeah, so I recommend try and do the other calculation as well. Try and calculate it where you'd forgotten the 2, the 1 over 2 that is. So when you calculate the determinant without the half there, you actually get a matrix with determinant 8. A common mistake is to reduce that by a half. No, you reduce it by 1 over 2 to the power of 3.
Yeah, and because really it's much easier. I think it's much easier without the fractions. You're going to get to 3 plus,
So it's going to be 2 times 3 plus 1, 2 times 4 is 8. So that the determinant of that is 8.
Yes.
So you should be able to see what the rule is. This is just another way to do it. I thought that seems nice, I'll do it this way.
And another comment, I'm sure you'll recognize this rule I've used when I did the cross product. I only use the first column, but I said as I go down the first column it's plus, minus, plus. So we make the cross product look like a determinant because we're using the exact same rules.
Yes. Okay, so next part is
I'm returning this.
Thank you. It's just do a calculation. Find what happens when you multiply R by its transpose. Now, we also still need to be careful about this half. It is there. And in this case, I won't bring it inside. I guess I could, but I want to try. I would like to avoid the fractions.
Let's avoid that. Plus, I think we're trying to show them efficient methods. So really, if you're lost and you don't know what to do, bring it inside. Now, if you can keep it on the other side and work without fractions, ta-da, that's what Josh is going to do for you right now.
Okay, so find R transpose. Now, this really just is going to be a calculation, so let's copy down R. It's going to be 1/2 root 3, 0, 1, 0, 2, 0, minus 1, 0, root 3, if I read correctly, yes?
Yes.
And the transpose, now here we do need to be careful, there is a factor of 1/2, so when I take the transpose, that doesn't change anything. And I could either write this matrix with a transpose symbol, but I'm just going to transpose it as it is. So that really just means flipping it about the main diagonal. So I'm going to take it, really that just means these are the only non-zero things, flip them over. So they're going to swap places. So this root 3 doesn't move, the 2 doesn't move, this root 3 doesn't move, and these two swap places. So you'll end up with a 1 here and a minus 1 here. And I guess these zeros also moved, but they were 0, so we didn't notice. Alright, now first things first, let's take care of these fractions. Let's just pull out these halves. The scalars are just going to sit out the front. So you get 1/4. And I think I will write it out again. It doesn't take me that long. I feel like it does make the explanation a little bit clearer. And now it's just time to do our calculation. So you should have a fairly good grasp of matrix multiplication by now. You're multiplying rows by columns. So I'm going to take this first row and multiply it by the first column. So root 3 times root 3, that is going to be a 3. A 0 times a 0, so I'm working across the first row down the first column. So 0 times 0 is 0, and a 1 times 1 is 1. Alright, now to get the first row second column, it's again first row second column. So that's, well, that's a 0. A 0 times 2 is a 0, a 1 times 0 is a 0. These are all 0. So I get 0 plus 0 plus 0, it's all just 0. The last one, well, this is the one, I will write this down. You get a minus root 3. You'll get a 0 times 0 again, so that's not anything, and you'll get a plus root 3.
Okay, ignore me for now. I just want to show you another way of setting this up later. So
Okay.
I don't exist.
Sure. Next one, so we're going for the second row, so let's take the second row and multiply it across. Now it's quite nice because you actually get 0, 4, 0 straight away. So 0, and then you get 2 times 2, which is 4, and finally 0. And now last row, so last row first column will give us the element in the last row first column. So it'll be a minus root 3 and a root 3. Next one will be a 0, 0, 0, because minus 1 times 0, 0 times 2, and root 3 times 0. Nothing contributes. And the last one is going to be minus 1 times minus 1. So it is minus 1 squared, but I'm just going to write 1. A 0 times 0, that's nothing, and a root 3 times root 3 is a plus 3. And you can see that these terms cancel out. In fact, it's very nice. You get that this is, well, this is a 4, a 0, a 0, a 0, a 4, a 0, and a 0, 0, 4. And I think we should simplify that because there is a common factor of, well, there's a 4 inside and a 1/4 out the front. This can be written as, well, it's the identity matrix. Let's just say that. It's going to be the identity matrix. So that's really nice. RR transpose is the identity matrix. Now, Laure's going to show us
Yes,
magic.
I wrote too high, so it's hidden behind the question.
Oh, I can raise the question up.
Oh, okay. Yeah, so that would be good. So I'm not really good at mental math or any of that. And so matrix multiplication I can find tricky. And so when I find it hard to multiply my two matrices if they're written like that. So what you can do is keep the first one. So I just copied this one and wrote it there. That's my 2R. And I took this one, and instead of putting it there, I put it up. The reason for doing this is now, if I want to know what goes there, I just multiply those, and they see this, 2 lines, and up. Tell me, if I want this entry, I take this row and, this column and this row, and I'm gonna get 3 plus 0 plus 1. That's a 4. If I want to know what goes there, it's gonna be this column and this row, so that gives me a 0, a 0, and a 0. So I find it slightly easier. So maybe I'll just finish the first column. Or maybe I pick a random one. Let's say I want this entry. So it's vertically right below this one, and I'm going to be using those. So I see exactly what I use, and then I can follow with my fingers. So 1 times 0 is 0, 2 times 0 is 0, square root of 3 times 0 is 0. That's a 0. So if you're not, so if you find it a little bit hard to see what exactly you're using, maybe this could help you with computation. And of course you get the same results.
Yes. I mean, actually I like this, but it points out something which I always tried to point out when I was teaching this, is if you pick any of these elements, so let's say I want the one in the third row, second column, then it's the third row of this matrix times the second column of this matrix, which is exactly what this does. It's a really nice way of seeing that. I like to actually internalize that. That's why I do it this way, because I go, I want this entry. Well, I want the third row, second column. Take the third row, second column, and then I just put it all together.
Yes.
So, I mean, it's the same thing.
Yeah.
That's quite nice because you see it happening. But I still would like people to see what's sort of happening on that
maybe
level.
that could be step one until you get familiar, and then when
Yeah.
you grow up, you can do that one.
Yeah. So I never learned that one myself, but it is a technique I see very often.
Yes, and yes, I've shown this in tutorials, and the students seem to like it, so I thought I would just show it there.
Okay. So this is actually part B, not part A. And we want to finish off. So the only real thing I'll keep here is that we've found that R transpose is the identity. It's a long calculation, but that's what we found. Now, the last part looks quite complicated. You have these other matrices. So I think it's got a matrix called P, which is P and Q, which are both invertible
Let
matrices.
me clean and talk. I can clean while you talk, maybe.
So we have P and Q. They are invertible matrices, and they're the same size as R. So we have these 3 by 3 matrices, and it just says simplify the following expression.
I'm sorry, I erased the thing you wanted to keep.
Yes.
I'll put it back in.
Thank you.
R times R transpose is the identity.
Yeah, so it's actually really why they get you to do part B. They want you to know this fact. So let's just write down the expression again because it's nice to see it. So we have Q times R times P, Q, R, the entire product, their transpose. So P, Q, R, and then the transpose of that, and then R, P inverse transpose. Now, we do need to know a little bit about how transposes work when you apply them to matrix products. So I'm just going to write down a general fact here. So you have that if you have a product, AB, and you transpose it, you are guaranteed to get B transpose A transpose. Now, it is very important you get the order here correct. So when you take the transpose, the B now comes first. So I might make this very explicit. This is not going to be the same as this. Definitely not. Unless A and B are special, but we don't know anything about these. In fact, sometimes you'll have it that this is defined and this isn't even defined. So yeah, don't use that rule. Now I can actually see two ways forward. I have the product of two transposes, and I know what I can do with the product of two transposes. I can put them inside the single transpose. Or I can do it the other way. I have a transpose of a product. I think I might do it where I'm going to take this and just apply the transpose to the product, see what it gives me. Now, at the risk of going too fast, I'm actually using a slightly more general rule. Maybe I shouldn't, but this is going to be QR, and when you have the transpose of the product of three matrices, it's pretty much the same rule. You reverse everything and take their transpose. So you have R transpose, Q transpose, and P transpose. So I've just reversed this and taken the transpose of everything. And I might as well do the same thing here. So I'll get P inverse transpose R transpose. Now, as it stands, if I didn't know anything special, well, there's some simplifications I can make, but the first one I want to make is, I notice this is the thing we worked out before. We know that R transpose is the identity. So this is really just Q times the identity matrix, Q transpose P, yeah, I'll do it in 2 steps. So that's just using one of the facts that I knew. Now, that's not going to affect anything. And I need to somehow multiply these two together. Now, it is true, actually, that the inverse of the transpose is the transpose of the inverse, but I'm actually going to do it slightly differently. I'm going to use this fact here. I know what to do with the product of transposes, so I'm actually going to work it into one thing. So this is going to be Q times Q transpose, just removing the identity, which doesn't change the product. the product of these two transposes is the transpose of the product, but in the opposite order. So I've used this rule, but I've used it in reverse. And finally, we just have an R transpose on the end. Now that's nice because P inverse P is the identity. That's what the P inverse does. So this is Q transpose, the identity, and I suppose to be precise it is the identity transpose, times R transpose. Now the transpose of the identity is still the identity. So this is, I could have just written the identity. Depends on how careful you wish to be. And finally, it's Q transpose, transpose. And I didn't know anything special about Q. I knew something special about R, but Q I don't. So that's as far as we can go. You have any comments or?
No. Just we got an extra question asking us to prove something that's not in the test. So do we do this in the end if we have time? Do we do this in consultation time?
Might have to do it. If we haven't seen a problem before, it might be hard to do on the fly.
No, I think we can do it on the fly, but I think it kills the problem for others who may want to think about it.
Yeah, so maybe there's still a lot of
pre-exam things. So let's do the exam.
Yeah, come to the pre-exam consultation.
Yes,
and try and ask the question.
So the question was if A times A transpose is 0, that implies A is 0.
Mm-hmm.
And yeah, so if you think about it, try to get an idea, and then come see us during the consultation, and we'll deal with that.
Yeah. So I mean, I can think of something which I think doesn't work. So.
Well, no, I have an idea that works. There's something more. Okay.
Okay.
So it's you again.
Is it her?
Yes, it is. You're doing a lot in a row. Unless you want a break and we can change the order.
No, this is fine. I think your question, the plain question, was very long.
It was.
Right, so what is the next question?
It's the one with the mean value theorem, which I haven't put
yes.
Sorry, yeah, because I said do it and I don't put it up. That's question.
So it's file number 12?
Yes, yeah. It's file 12. 2 files up, so just 12.
Okay. So it looks like a very short question. It just says state the mean value theorem and use it to prove something. That being said, the mean value theorem is quite a long theorem to write down well, not as long as some theorems I've read, but when you're first starting to learn about theorems, probably it looks like a very long one to write down. There are many parts to it. So I was thinking about how I would attack this. So I actually might start putting it together in maybe a very non-linear fashion, which is, let's start, say, let f be a function. Now I'm being intentionally bad here and saying I have a function and then I have f of b minus f of a over b minus a is equal to f of c. Now I would expect to see a lot of people do this as a first approximation to this question, where you say you have a function and this happens. That's not good because you haven't really told me anything about the function or what even how this c relates to these a's. So first things first, this theorem applies to differentiable functions, but functions which are differentiable over a certain interval. So I'm going to add some information about f here. So let f be a function.
So if you think this is the theorem, you're really missing a lot here. We really need to know when it works, what c exactly is. As you can see, there's an f dash. So if the derivative doesn't exist, there's not a single chance this is going to work.
So this is still a poor approximation to the theorem, because I say let's have a differentiable function. Well, actually, the theorem doesn't just say let's have a differentiable function. It says let's have a differentiable function over, and it's an open interval. And actually, I might add that word.
The open interval, so everybody remembers that.
Yeah. So let's make that very explicit. The notation tells you, but let's make it very explicit. So over the open because it's very important that we know it's open. Interval A, B. Alright, that's a bit better, but actually we don't have any control about, I think I'm in the way, we don't have any control yet about what is happening at the endpoints here. And we do need a bit more there. In fact, I would probably state this first. So we have a function which is, so let's take a function, and I might
as you can see
restate
from
this.
now, we only said what happened in the open interval AB. So really anything can happen at A and B, and I tend to believe that if anything happens, this won't work, and indeed it won't.
Right, if I was writing the exam, which thankfully I wasn't, I would actually put a question where you should try and sketch something which one of the conditions fails for. But I didn't write the exam, so I'm pretty sure that won't be in there. But let f be a function, and we need to say which is continuous over, and again being clear, it's a closed interval. So we're including the endpoints A and B. And it's differentiable over the open interval AB. Very, very close, but we have to say something about what this C value is. So if we have this set up, then there is a C value in the open interval such that this is true. Have I missed anything?
No,
It's all there?
No, I just maybe wanted to. So you're going to do a picture?
I probably should, yeah. I mean, the picture would also explain. Maybe you can...
What I wanted to do on the picture is I think we're trying to turn you into mathematicians. So I think when you have a theorem like that, and you don't really believe, or you're wondering what the assumptions are for, you should actually try to see what happens if I decide, do I really need the thing differentiable? So what your theorem really says is, okay, you have some, the version which works. So that's your A, that's your B, and f of B minus f of A on B minus A really is the slope of the line connecting those two, and it tells you, well, there's a point where you can actually get the same slope.
Yes, actually, I should point out, I think mean value here refers to the mean slope, doesn't it?
Yes. Okay, so let's see, would that still be true? Let's try to remove the condition that the function is differentiable. So I want something parallel to that. If my function is like that, at no point can I find a line parallel to that, and the problem is it's not differentiable. So you look at that and you say, I'm convinced, I need that. And I'd like to try to convince you that you also need the other one. Okay, let's remove the condition it's continuous on the closed interval. So for example, instead of stopping here, so A, so that's going to be my A, and let's say my function goes like that. So that's my function, and it's continuous on the, I wanted to line them up, failed miserably. So if it looks like this, you can see that there is no tangent parallel to that, and the problem is that here my function is not continuous on the closed interval, only on the open one. So you should have a few scribbles that tell you, yeah, this theorem is not going to work unless I have these two conditions.
Yeah. So
which is why you're not getting full marks if you don't have all the conditions.
Because it's not true.
Yeah.
Let's see. Actually, there is a quick question someone came up with about the last one. Can't we simplify QQ transpose to the identity? Well, no. QQ transpose, typically that's nothing special. It looks nice, but unless you have a special matrix, QQ transpose won't be anything at all. We were lucky that RR transpose was the identity. Part B told us that, but in general that's not true.
And we had to perform a calculation to actually prove it was identity.
Yes. I guess it looks similar. QQ inverse, that's the identity, but QQ transpose is not the same thing as QQ inverse. So don't get those two confused. Right, so let's continue on with this question. We want to prove an inequality about the hyperbolic sign. And it just says, prove that the hyperbolic sign is greater than x for positive x. And somehow that all comes from this theorem here. Now actually, I think these sort of questions they're very common in the notes, so you should have had a lot of practice doing things like this. So it's all really about the setup. Now I've seen people do this in various ways, but I think the way I'm going to do it is just pick my function f to be the hyperbolic sign. So let f, well, let's say, I don't really like this way of defining a function.
That's okay.
Yeah, I think I'll live with it for now. So
Yes.
I'm defining a function here, which, in fact, I use x, because working through these proofs in the past, x is usually the thing in the interval, not the thing defining the function.
Yes, your
so
x is going to be fixed.
Yeah. So let's let our function be this, which is, well, let's just state we know that the theorem's conditions are satisfied.
You're suddenly writing much smaller than you used to.
Oh, yes, I am.
That's okay. You said it, but maybe later on you write bigger.
I think this sentence, let's just get in a better habit. So, which is continuous over, well, it's continuous over the interval. Actually, it needs to be a closed interval. We'll discuss that.
Maybe you should have started with picking an x. Let x be any positive number which would go above, and now that x is chosen, let's use this interval 0x, but you need to say that you picked an x.
So it'll be that. So Laure's right. This is less than ideal because I'm talking about something and I haven't defined. It has to be special. So
just
I should
push the blue line just 1 centimeter up, and no one will ever know.
So yeah, if you are writing this in the exam, you can easily just add a new sentence to this, right? So there's just one thing. I need x to be a strictly positive number.
Yeah. So if you want to prove that something works for every x, what you can do is, see, I'm picking one which has nothing special, and I can prove it works for this one. Therefore, it works for all of them. So a lot of your proof that they prove that something works for all blah 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 will start with let, and then you choose one of them arbitrary and do the proof for this one. And from now on, it's fixed. So when you say this, it means I've picked an x, there's nothing special, but now it's fixed. So we can use it in the theorem.
Yes. So it is continuous over this closed interval. It's differentiable over this open interval. In fact, the function is differentiable everywhere, but because I'm using the theorem, I'm just saying this is the important part. It needs to be differentiable over this interval. So I'm writing that down. Then, well, the mean value theorem tells us something. It tells us that there is a c in this interval such that this is true. Therefore, this is by the mean value theorem. There is a value c in the interval 0 to x such that, well, we're going to have the shine of x. So here, the upper end of the interval, there it was called b, here it's called x. So shine of x, the hyperbolic sign, minus the hyperbolic sign of 0 over what was b minus a, but in this case is x minus 0. Well, that's going to be equal to, well, the derivative of the hyperbolic sign is the hyperbolic cosine. So it's going to be the hyperbolic cosine at this value c. Now, this is going to lead us quite quickly to the answer, because we know what the hyperbolic cosine looks like. And I might just do a quick rough sketch over here, just to remind you. So let's say this is, well, let's say this is c, and this is the hyperbolic cosine of a c value. The nice thing about the hyperbolic cosine is it starts at 1 and it just increases in both directions. So this is something I think you should just know from learning about these hyperbolic trig functions. You know that Well, I know that the hyperbolic cosine is always greater than or equal to 1. Actually, it's even better for us, because since we don't include 0 and x is a strictly positive number, it's always strictly greater than 1. So I might actually add it to this sentence here. We have this value here, and I observe it's always strictly greater than 1. Now the hyperbolic sine, not hyperbolic sine, the hyperbolic sine, also known as sine, of 0 is 0. So this is really sine x over x is a number greater than 1. Where's the best
right below the graph
here? So, well, what I have so far for this positive x value, the hyperbolic sine of x over x is a number greater than 1, strictly greater than 1. And, well, because x is positive, if I just multiply, well, scaling by a positive number keeps the inequality. So that gives me the hyperbolic sine of x is greater than x. And I'm also going to add the reason here why it worked. Just reminding us, since x is a positive number. And I think that's all that's required.
Yes. And I think it's a good idea that you check, because there will be cases where you actually need to prove an inequality for negative ones. So make sure that every time you multiply an inequality, you just check the sign of what you're multiplying by.
Yes, I suppose it would be curious, maybe as a little exercise for yourself, try replacing this with x strictly less than 0.
Ones?
It would be curious to see what happens, and this will still be true actually, because there's nothing.
Yes, up to here it's right, but then you get less.
So yeah, this will be the step you need to be careful. So do try that. Try replacing this with the other side and see what the result you get is.
Which makes sense, right? Because the curve is like that and the tangent is x. So try to check also that it makes sense on a graph.
Yes. Okay.
Question, comments? I don't see anything in the chat. How do you choose?
How do you choose the best f of t? Mostly I think it's experience, because you should have done these problems quite a lot. They're all in the tutorial problems. You did them in the online tutorials, I definitely know that.
Well, and for this specific one, you want to say something about shine. It seemed like the only reasonable choice.
There is another choice, but...
Sometimes what I do is I try to rewrite the conclusion. You know, it's really, you find it hard to know what to do. So what you want in the end is shine x greater than x. And I know I'm using the mean value theorem, so I want to make it look like that. So in my head or on scrap paper, I'm going to divide. I'm going to divide by x, which is positive, so this works. And at that point, and maybe that's where the experience comes in, but I mean, you know, if you're using the mean value theorem, I'm going to say, this really looks like, oh, I can subtract 0, it makes no difference, and x minus 0. And it looks even closer. And at this point, I know it's going to work. So I don't spend too much time doing this on a piece of paper. But that's my rough working. I get this rate of change. I'll say, okay, this is going to work. That's the right function.
Yeah. So...
And there are exercises, I think, in the notes that we did in tutorials, for which it's really a good idea to do this first, because it's not that easy to spot the function. But once you manage to rewrite it this way, you know it's going to work.
Yes. Okay.
You again.
It's me again.
Yes, it's you again.
And then you'll finish up the lesson. Okay.
Yes, exactly.
I'll go get the image up. So I think I might have to first just talk about what the question is saying.
Yes.
And then I'll have to actually show the question. The question has a lot of things there. There are, so it says you have a graph. So you have a nice graph there of a function which is differentiable. So you can see at the top there it says that the...
Did you want to explain if you go there?
Ah, yes.
Yeah.
So, and I better read it from here because my eyes are not good. So we have a function and it says that it's a differentiable function rising from the origin to the point A, B. So it's increasing and it is differentiable. So you know you can take a derivative of this function. And then it says the graph is cut by a vertical line, and it gives us this shaded region as pictured. So the shaded region is bounded by y equals f of x and x equals t, and the x-axis together with another shaded region. Now, it's a lot of information, and then say we have this area, it depends on where this vertical line, depending on t, is. Write down an integral which calculates the area for us. In fact, it says show that this particular integral we give you will give you the area. I guess it's difficult to use.
Yes, I would like to use that thing.
If you're not selecting the right image, it doesn't work.
Yeah.
Right.
Sorry, it's a Mac. I've never touched a Mac in my life.
So I'm going to...
Can we make it a little bit smaller? Because I think they could still read. You can reduce it.
Maybe I'll keep part A. Yeah. So let's just do part A to begin with. I'll just raise it up.
Yeah.
So actually the first part is not very hard. The first part, basically you just need to recognize how to get the area of this shape from integrals. So I might actually copy the picture down myself, and so I can refer to what areas I'm calculating.
And also with bigger
Yes.
bigger letters on the axis.
That's very dark.
Yeah, you picked an invisible marker.
Right, so we have our, that's better. This should be our y-axis, and we have our x-axis. Now our curve, they tell us it starts down here nicely at 0, 0, and it's just differentiable and increasing, so it could be anything. It's just differentiable and increasing, and at some point AB, well, that's where the sort of curve stops. And then we're going to get an area, so we have some value t, which gives us a nice line. And we're going to get this area here. Wait, I might give this a label. This is why I like making the picture. I'm going to call this A1. It does depend on t. Maybe I should say A1 of t. And there's another area up here, which I'm going to call A2, which also depends on which particular t we've chosen. Okay, so the reason I'm doing this is just because I find it easier to write down the integral for this area to begin with. I guess maybe I'll just label this y is f of x. That's the graph. Also, one more thing. Of course, this is b. All right, so because I did draw the picture, I guess I'll say the area labeled A1 in, and it's not, I'll be very precise, it's my diagram, not the one in the question, is given by, well, this one's quite easy. So A1, it does depend on t, but it's a fairly standard integral. I'm going to be integrating from x equals 0 up to x equals t, the function f of x dx. So that's fairly easy, I think. This other one is going to cause us a bit of problem. Now, well, the thing we were integrating before is we were integrating this height here. So we were actually integrating from 0 up to here. Now I want to be integrating from this curve up to here. And this height here, the above here, is b minus, so let's say, I'll draw more as not a vector, as a distance. This distance here is b minus f of x for some particular x value, or, yeah, I mean, whatever x you're looking at. Okay, so then the area is quite simple. You're just going to be integrating this height over this range from t up to
A. So
A.
maybe you want
Yes,
to.
I need to also add that, I think.
Yes. But I don't think the students will be very surprised by that, because I think we have a theorem in the notes that say if you want to calculate the area between two curves, you you integrate the curve at the top minus the curve at the bottom between your points of intersection. So that's just what it is.
Yes. So that's the area labeled A1, and I don't want to say likewise, and not really likewise, I feel, and the area.
Maybe you can just say, and A2 is.
Yes. Sometimes wanting to be very explicit does actually harm me. But the area, so the one labeled A2, which again, it does depend on where t is. We're going to be integrating from t up to a, x equals t up to x equals a, of, well, it's going to be the top curve, b, minus the bottom curve, f of x. Now, if you look at the question, that's not quite what they wrote for their second term. Their second term looks a bit different. They had the t at the top. Well, thankfully, we know how to swap the interval. Well, what happens when we swap the endpoints of an integral, it just puts a minus sign. So this is really minus the integral from a up to t of b minus f of x dx. And there's no really any point, there's no point to leaving that outside. So I'll work that inside to get the integral a to t a minus b plus an f of x. It feels like that makes more sense to write that as f of x minus b dx. Alright, so that's my first area, that's my second area, and I'll just put it up here. Hence, well, the area, which is the sum of these two areas, so the total area of this diagram, is going to be a1t plus a2t, which is just what I've shown. It's what they asked for. Integral from 0 to t, f of x dx, plus this other term, the integral from a to t, f of x minus b dx. Alright, so that's just the formula they gave us. Now, okay, that's nice. And kind of one reason we're doing this is because what we're about to do in the second part of the question. We'd like to use the first fundamental theorem of calculus. And if you do look in the book, which I suggest you go and do, the endpoint, the sort of the variable endpoint in that integral is always the upper limit. So it makes sense for us to put it there just to make it more familiar. Now I need to get the, it's hard to see the question.
Okay, so I'll just label while you want. So while Josh is fixing this, we had a question about the previous exercise. Why is cosh of c greater than 1 rather than maybe equal to 1? And the reason is you knew that c was between 0 and x. So c cannot be equal to 0. And if you look at the graph of cosh, the only value for which you can get 1 is 0. And 0 is excluded. So you know you're getting something greater.
Yeah, so that is very important to understand why. Because without knowing anything, all I know about hyperbolic cosines is they're greater than or equal to 1. But if you're away from the 0, then they're always strictly greater than 1. Right, so the second part of this question, it's giving us a big hint. Use the first fundamental theorem of calculus to show that this area has a local minimum at the point where t is equal to the inverse, f inverse, of b on 2. So really, I think the fact that we're looking to show that there is a local minimum kind of indicates we're looking for stationary points. So we really want to take derivatives of this. And I mean, it says use the first fundamental theorem of calculus, which tells you how to take derivatives of an integral like this. So it should be clear what they're asking. Take the derivative of this and see what it does. Find a stationary point. Okay, so let's just take the derivative of that.
Maybe you can label the question B just for it's easier for people to refer to this.
And I might start the work over here.
Yeah.
On screen. Yes, just.
All
right. So we're looking at. I might just start with the derivative. We're looking for dA dt. That is just going to be the derivative, well, of the expression we have. Now, I like this question for two reasons. It's a nice question, but also they've given you a of t. So even if you couldn't quite do part A, you can still do part B because you know what the result you're starting from. So that's very nice. And it's plus integral 0, not 0, integral from a to t of f of x minus b. Alright, now I'm going to split into two derivatives just to make it so it's very clear where the fundamental theorem of calculus came in. So we're asking for the derivative of this integral. And we're also asking for, so we're adding on the derivative of this. Oh, that was very bad of me. I dropped the dx.
Yeah.
So yeah, keep an eye out for your own mistakes. It's good to see them. So a to t, yes, f of x minus b dx. Now this is precisely what the fundamental theorem of calculus tells us about. If we're integrating a continuous function, then when you take the derivative of this integral, you just get the integrand back. You just get what's inside. So I don't think I want to say too much more than just this is going to be f of t. And this term here is going to be f of t minus b. It's the integrand evaluated at that endpoint. So that's nice because that simplifies to twice f of t minus b. Alright. So this will only be 0 if we can get a point where twice f of t, well, yeah, where this is 0. So we're looking for a stationary point of that. Now, I might keep this up and just get rid of this thing below.
Yeah.
The diagram would be too hard to recreate, so I better keep that.
So just a comment while Josh is erasing. This way of taking the derivative doesn't work all the time. You really need the variable you want to differentiate with respect to at the top. If it's at the bottom, do something. It has to be the plain variable. It can't be t squared, it can't be t cubed. If it is, find out, there are ways around, look in the tutorials. So that's why we had all this work initially to rewrite the original area in a way that seemed unintuitive. The goal was to get the t at the top.
Yeah, so that's... Alright, so for part B, we're trying to find a stationary point, and there'll only be a stationary point if this is 0. So this is, hence, we will only have a stationary point can't spell station apparently. Try that again. Stationary point if we have twice the f of t minus b is equal to 0, which is the same as asking for f of t equal to b over 2. Now, actually what's nice is this is guaranteed to happen if you look at our diagram, because b is up here. I'm just looking for a point halfway down. So b on 2. What's actually even nicer if you look at this question, there's only one place it can happen. The original question said this function was increasing. I guess it could be multiple points if it's sort of like 0 derivative. So maybe it should say strictly increasing, but in any case you do have... Ooh, was it strictly decreasing?
I think increasing in English means strictly increasing.
Okay, yeah, actually, remembering how the next part goes, it does need to be strictly increasing.
It is strictly increasing.
Okay, strictly increasing. So there will be a point where this happens. Yeah, I guess I do need to refer to the inverse function theorem. It seems like appropriate to have this one-to-one function.
And that's a question you should ask yourself. Sometimes, because some functions have an inverse and others don't. So if you want to say that, if you want to use the inverse and it doesn't say in the question it's invertible, then it's your job to explain why we are allowed to use the inverse.
So I might use that discussion we just had actually, that because f is strictly increasing, it's actually not quite sufficient now that I think about it. Because f is strictly increasing, I might add one more thing. The one thing to make sure it really does work is the continuity.
Yeah.
And continuous over a, well, over the interval.
Over 0a.
Yeah. There will be a point. Well, actually, no. That wasn't the point of the discussion. The point is f is invertible.
Yeah, they will, exactly. Because
that's what I meant to
we
say.
want to prove that we are actually allowed to use the notation f inverse.
That f is an invertible. In fact, why did I make that open? That should be closed.
Yes, that's what, yeah.
So is invertible. Word I can't spell very well. Able? I think there's an I somewhere. That's what I thought. Spelling's not my strong suit. So is invertible over 0 to a.
Yeah.
So, okay, so hence, well, I guess.
And then basically you're applying the function f inverse to both sides of your equation. And you get the actual value of t.
So hence, well, I might just say hence that exists. I think if someone did an exam, I would be happy to see this. The fact that you realize this is an invertible function, there will be a point where this happens.
Mm-hmm.
All right, well, that only finds us a stationary point. It doesn't tell us what kind of stationary point. It could be a point of inflection, it could be a maximum, it could be a minimum. The only real tool I have at the moment for interrogating that, I think, is to use the second derivative test. At least that's the one that jumps out to me. And that's nice because the derivative is this, and I started with a differentiable function. In fact, I kind of cheated here. The continuity here is a consequence of differentiability, so it is a continuous function. But yes, we have that, so we can take a second derivative of a quite nicely. I suppose that's going up here.
Yeah. I mean, it's probably not the only way, because you could say f is increasing. So once it passes the value where it's equal to 0, then it's going to be positive after that and negative after that. But I think it's more writing. Whereas since your first derivative is nice and easy, taking the derivative of the first derivative, and of course you check in the question that it's allowed.
Yes.
And in the question they said the function is differentiable. So
that's actually hidden off at the top.
Yes.
So
yeah, but okay, so you check, and really that's the first derivative of the area, so now you can differentiate once again. And you do.
So because f is differentiable, we can calculate. So I'm looking for the second derivative, which is quite nice because it's just going to be the derivative of that expression, twice f of t minus b, which is twice the derivative of this function. That's allowed. And here's where I think it's very important that it's strictly increasing, because if this is strictly increasing, then this value will be positive for all t. So you will have that this is, so I'm going to say greater than 0 because f is increasing. I prefer strictly increasing, but that's what they mean.
I do, but I thought in English I couldn't. I've learned something today.
Well, I think it's just, it's like standards.
Okay.
People have their own standards. Increasing, it's, yeah, I guess it's the difference between non-decreasing and increasing. This means increasing and strictly increasing.
Yes, strictly increasing.
So because f is increasing, that's why we have that. And that's actually what the second derivative test needs. The second derivative is positive, so it's shaped like a nice positive smile. So hence, by the second derivative test, I hope I'm not blocking this out. Might be. Nope. Hence, by the second derivative test, this point, or maybe I should be explicit about what point I mean. The point t equals F inverse of b over 2 is a local minimum. All right.
So we got a question about what the first fundamental theorem of calculus says.
That's very important.
Really exactly that. Maybe you didn't recognize it because the letters are swapped. The way it's usually written, you have a function of x, agreed, and your function of x is defined as an integral starting from some number, not really important what the number is, and ending at x. And as we said, plain x, only x. And inside, you're integrating something. And what your first fundamental theorem of calculus is, if your function looks exactly like that, and the one inside is continuous, so you need the one inside to be continuous, then, so I'm just skipping details, then you can take the derivative of this one with respect to x, so your number at the top, and the way you get that is marvelously easy. You just basically drop this wherever you see t. So that's what we've been using here, except that the letters are swapped compared to what we normally do.
Yes.
You need to go check exactly what the assumptions are, because you will need to be able to check that they are satisfied.
Yes. So I think, yeah, so it was necessary. No, actually not here. Somewhere else it was mentioned, and we did have the
Yeah. So f continuous is what you need.
Yes.
The
F
inside
being
function.
continuous is what we need. Actually, I can't remember if I did mention it or I skipped over that fact. I might have.
Yeah.
Okay.
So I don't think we have any more questions on this one. So last one.
Very last one.
And that is mine. Your pen seems better than mine. It's this one there. It's wider, I think.
Yes, that's that one.
Okay. So one of the main reason we wanted to do this one is to cure some maple phobia. Some people see maple and they think it's going to be hard. I can't do maple. If you've never seen maple in your life, do you really think this one is hard? Maybe, I don't know, it's the font or what, but then see, your question is rewritten in a very easy way. Basically, what maple tells you is f of x is defined to be 0 if x is less than or equal to 0, and exponential of minus 1 on x if x is greater than 0, and it's written as that. I'm writing it for me because I'm going to use that. And again, same thing, even if you're not sure about the syntax, it's really easy to guess that g of x is f of x times f of 2 minus x. Right, so that's your definition. And then you have the plot, which could be useful. So really, it's not a maple question. The question has been given in maple format. It's just defining your two functions. We're not really using maple. So we want to show that the function is continuous at 0. So for a function to be continuous at 0, you need to have the limit of the function at 0 of f of x as x approaches 0 to be equal to the value of the function at 0. That's the definition you have for continuity. It just turns out that for this specific function, it looks different on the left of 0 and on the right of 0. So the way to explain that this limit does exist is to say that the limit when x approaches 0 from the left and when x approaches 0 from the right are equal. So this becomes the limit as x approaches 0 from the right of f of x. That's really x is 0 plus a little something, so it's from the right, is the same as, the limit of f of x as x approaches 0 from the left, 0 minus a little something, has to be equal to f of 0. So proving that's not exactly what I wanted to write. So maybe I wanted to say f is continuous. I'm going to cheat. Hops, creating some space. F is continuous at 0 if and only if this happens. So actually what I wrote before, it's the same as showing that as x approaches 0 is f of 0, and I would say you will choose one or the other depending on the question you have. If your function is defined piecewise, meaning you have a different definition on the left and the right, that comes handy. If you have the same formula for the left and the right, maybe you would rather use this one. So what this is saying, there are three numbers. If they exist and they're equal, it's continuous at 0. So your hope is to see that maybe one of them doesn't exist, or the first two you try to calculate are not equal, and that's the end of the story. Let's do the easy one. What's the limit of f of x when x approaches 0 and is greater than 0? So from the right. No, I said let's do the easy one. I'll do from the left. So from the left. And then keep the marker in mind. The marker needs to know which formula you're using. They need to know if you're looking in the right place. So don't just write the answer even if it's obvious. I want to say x is negative, therefore I'm using that. So I'm writing here, that's what I'm using, and of course I get 0. So I calculated this one, and this one is 0. So it exists. F of 0. I just look at the definition I have, and it says that f of 0 is calculating using the first formula. So these two numbers are equal, and I need to calculate the third one to see if it's equal to the other two. And I will do the same thing. I'm going to indicate which formula I'm using. And I'm using this one there, which works for positive 1, minus 1 on x. Okay, so I need to explain how I do this. You said orange was good, right? So if x approaches 0 from the right, that means that 1 on x is going to approach plus infinity. So I'm just trying to see what I'm going to do. So that's exponential of minus something that goes to infinity. So this is just for me to help myself. Now I try to write it better. So that's the limit of exponential of minus something. So I call the something y, and the something goes to plus infinity. So what I've done here is really a change of variable, if you'd like. Y is equal to 1 on x. And now we recognize a well-known limit just looking at the graph of exponential, and I get 0. And now,
it's not a question yet, but there's one that I'm asking myself because I see it in marking. What do you say to somebody who writes down equals e to the minus infinity?
That's not the correct notation. I've never seen it.
I've seen it in exams, and I don't like it.
No.
I've seen people use it. It's just we've never.
No, it's like you're treating infinity like every other number. And if infinity was like every other number, then infinity plus 1 being equal to infinity, you cancel infinity, and 1 is equal to 0, and it's a disaster.
Yeah.
So
that's why you make us uncomfortable. At least you make me uncomfortable.
Yes, yes, exactly.
You're not treating the concept with respect, I feel. This is quite nice. Actually, I'm wondering, how do you feel about some other notation? Because I have written things like this. So I've written things like the limit 1 over x tending to infinity e to the minus 1 over x. It's what you've done, but I haven't given y a name. I think I prefer this, but I have.
This is much better, I think, because really you need to say something approaches something.
Yeah.
So, yeah, and really the way we think of this is exponential of minus infinity, if you like, so exponential of minus something that goes to infinity, which is exactly what we're writing here.
Yeah. So
And the idea in your head is that the something goes to infinity, so you just write the something goes to infinity.
Yeah. So I have sometimes written that, but I prefer this. I think this is much nicer. So,
yes, I like this one. And let's say, since we're crossing on the board, I'll cross this one out also. So the rule is your function is continuous if these three numbers exist and are equal. Well, the first one is 0, the second one is 0, the third one is 0. So you put all this together, therefore f is continuous at 0. just using the definition of continuity. Okay, all good. Next question. We want to show that f is differentiable at 0. So I'm just going to erase all of this, except the definitions. So first, in case you think, oh, you know, I've done one and one implies the other. Yes, one implies the other, but it's the other way around. If it's differentiable, then it's continuous. And what we proved is that it's continuous. So if we had proved it's not continuous, then there would be no point in trying to prove it's differentiable. But we can't use any general theorem. Continuous is weaker. If it's continuous, because for example, just think of a function like that, it's continuous, but it's not differentiable there because you can't possibly fit a tangent. So that means we have to do it by hand. So that's question B. And again, you can stick to the definition of differentiable. So f is differentiable at 0 means by definition that if I calculate the limit of f of x minus f of 0 on x minus 0 as x approaches 0, if and only if this limit exists. Right? And so in our specific case, it's the same as before. The limit, when, in general, the limit of any function as x approaches a exists if and only if you get the same limit when you approach from the left and the right. So I'm going to rewrite this condition. So f is differentiable if the limit exists, and the limit exists if the limit from the right exists, and the limit from the left exists by writing that, yes, I can write. Yes, I'm going to write they exist and are equal. So what I have here is a strategy. So I need these two limits to exist and to be equal. The plan is clear, right? Let's calculate them. This is, so again, like warm up, the one on the left seemed nice. So I calculate that, the limit as x approaches 0 from the left of f of x minus f of 0 on x minus 0. And again, I'm trying to show I'm not cheating. I'm actually using the formulas over there, and I need to show I'm using the correct one. So because x is negative, I get a 0 at the top. Sorry, I want to put limit. That's the limit when x approaches 0 from the left of 0 minus 0 on x. This is not an indeterminate form, in case you're wondering. Indeterminate is the limit of the top is 0 and the limit of the bottom is 0. At the top here, it's not a limit, it's a perfect exact 0. So it's really the limit of 0. And so we get 0. So that means that this one exists at least. We proved that this one exists, right? And it's 0. Well, now we need to calculate the other one, and that's going to be harder. The limit as x approaches 0 from the right of f of x minus 0 on x minus 0. So I can sub in using my formula over there. And I get exponential of minus 1 on x on x. Okay. So again, I'm going to, before knowing how to write it nicely, I need to know what the answer is, right? So this is going to approach plus infinity, so that approaches negative infinity. So the limit of the top is 0 and the limit of the bottom is 0. Okay, bummer. That's an indeterminate form. I will need to do something. So I can try the same thing we did before. Y is equal to 1 on x and hope it's going to help. If x approaches 0, 1 on x approaches plus infinity. And I'm going to get exponential of minus y. And my x is 1 on y. that looks good. I just need a little bit more space. Hopefully,
So
enough
the
space.
limit is the y?
Oh yes, it's the y, of course. Yes. Yeah. If I do the change of variable, I should definitely change everywhere. So I'm going to multiply the top and the bottom by y. So my y will go at the top. And I can, because I have a minus y, I can put it at the bottom. The reason why I'm doing this algebra is because I have something in mind. You have 2 seconds to find what? Should be thinking of that. You can get the result using L'Hopital's rule. Actually, you should know the result before you start. You should know that when we go to infinity, exponential dominates every polynomial. So the limit will be 0. And then L'Hopital's rule is a way of proving that. So if you use L'Hopital's rule, so I don't have much space, I'm maybe just going to write the result here. It means I'm going to differentiate it. I'm going to differentiate the top with respect to x. Can I just write L'Hopital's rule here? If I differentiate at the top, I get a 1, and at the bottom, I get exponential of y, because now my new variable is y, which also answers what you were saying earlier. It works much better if you actually do the change of variable.
Yes.
And remember that L'Hopital's rule work if the limit of the top and the bottom are 0, or the limit of the top and the bottom are infinity, and if the quotient of the derivative actually has a limit. So here it works, and we get 0. At that point, a lot of you have been focusing on limits and probably lost the plot. The goal was to prove the thing is differentiable. And we said it's differentiable if and only if these two numbers exist and are equal. And we just proved that the limit of the rate of change when you approach from the left is 0. And the limit from the rate of change when you approach from the right is also 0. That seems very good. So your function is differentiable. Okay, I was going to write under the question, but there's no space under the question.
Oh, I can raise the question up. So I can move it if you want. Or do you want the top?
No, because I'm going to start working on G, and so having the graph would be good. So I'm going to write the conclusion there. So my conclusion will be, so for question B, I've proved that the two numbers exist and are equal, therefore f is differentiable. At 0, and the limit of the rate of change is always the value of the derivative, and we found that this to be 0, and the derivative of f at 0 will be 0. We can't really check with the graph they gave us, because it's the graph, if you look, it's the graph of G, not the graph of f. Because hey, in case you've forgotten, there are two functions in this story. So I'm looking here now. Explain why G is continuous and differentiable everywhere. So in case you're panicked because you think we're going to redo all of that, no, let's calm down. We know already that f is continuous and differentiable at 0, and we're going to be reusing this. The question is slightly different. This time we want to have continuity and differentiability everywhere, not only at 0, but it turns out that there's no problem outside of 0. If you look at your function f, outside of 0, so on the left it's only 0, and on the right it's exponential composed with 1 on x. So these are, what's the name? It's the usual functions. They're not called usual.
The elementary?
The elementary function.
Composition of elementary functions.
Yes. So f, so if x is positive, no, gonna be better. So on 0 plus infinity, f is obtained from elementary functions, so usually using the 4 operations and using a composition. And we know that all the elementary functions, they are continuous and differentiable on their domain. I'm insisting on their domain because we include, for example, a quotient of a polynomial by a polynomial, so I never meant that this is continuous everywhere. Is obtained from elementary function, and as such, is continuous and differentiable. Sorry, my handwriting is not as good as Joshua's. And differentiable on this interval. So similarly on minus infinity 0. Right? So we have shown that, so in this specific part, we have shown that x is continuous and differentiable for values of x less than 0, for value greater than 0, and in the part above in A and B, we proved that it also works as 0. So combining with parts A and B, f is continuous and differentiable on R. And in case you think we haven't started, the question is not about f, it's about g. But then look at how g was built. G was built by, so here we apply the function which maps x to 2 minus x. So that's an elementary function. And then, so from that, so we created f of x and f of 2 minus x, which are two functions which are continuous and differentiable, and then we multiply them. And we know that when we multiply continuous and differentiable function, it's going to be continuous and differentiable. So g will also be continuous and differentiable as the product of two such functions. And that's the end of the hard question. The last one is much easier than that. So don't forget, when you have questions where you need to prove something is continuous and differentiable, you don't always need to go to first principle for differentiability, and you don't always need to calculate limits. In fact, in a lot of cases, you can just say we've been multiplying or adding or something function with those properties, and we have a theorem that ensures that they will be continuous and differentiable. Next question, calculate the derivative of g at 1. Easy one. So first, you should know what the answer is without calculating anything because it's in front of your eyes. You look at the drawing and up there you see that when x equal to 1, okay, it's hard for me to point because there's a lag, you get a horizontal tangent. So we must get 0. And I would say if I was marking, you make a mistake. When you have the drawing in front of you, you don't get 0, I give you 0. Because you had a way to check. Or at least you say, I know it's wrong because from the picture I should have got 0. Okay, let's not lack common sense. So, take this formula, and now I know that it's differentiable, I differentiate. If I differentiate this, it's just the product rule. So u dash times v, 2 minus x here, plus u v dash, and now when I do v dash, there's a function inside a function, so it's a chain rule. So derivative of the outside function evaluated at the inside function, which is 2 minus x, times the derivative of the inside function, and I get a minus 1. And now I can just, so what I'm going to get here, so I can leave it this way, and the question is only what happens for 1. So I sub in x equal to 1. If x equal to 1, I get f dash of 1 times f of 1, because 2 minus 1 is 1. And here I'm getting an f of 1 again, and I'm getting an f dash of 1, and this minus sign is there. And as predicted, we get 0. And that's finally the end of the live stream. We've gone way over time, but we thought this question was interesting, so maybe it was worth doing a little bit more.
Yes. I guess the important thing here is, actually this is a very general fact about the way g was constructed from a differentiable function. It doesn't depend really on the definition of f at all, just the fact it's differentiable, which is rather nice. I guess it also means that I suppose you could have worked out a formula from this and worked from the formula, but that would have been excessive, I guess.
Oof.
I mean, it would be too. Well, you'd end up with a minus 1 over x and e to the minus 1 over x.
Yes, we could work out a formula.
Could definitely do
and
it.
indeed, if x is negative, we get 0, which is exactly what we get on the graph. If x is more than 2.
Yeah. So
yes. So
yes.
Yeah. So if x is more than 2, this one is 0, and then in between you have a mix of those.
Yeah, it could be done, but you can see that this is the nicest way, I think. This is the way.
Yeah, this is going to take forever.
Yeah, there's always other ways to do problems. It's good to spot other ways, but I think we should agree that this is probably the best way. I can't think of a better way. I had one question that came up when you were taking limits. I'm wondering if students might think about this. So there was maybe I'll just write up here. So there's
Do you want me to get rid of the question?
Yeah, let's do that. So I'll start writing here. So at one point we were looking at the limit as x went to 0 from the right, and we had an e to the minus 1 over x over x. I think this was the problem you had.
Yep.
And this was heading to 0, and we also found that the top was heading to 0, so it wasn't indeterminate form.
Yes, it's indeterminate, yes.
So I guess there's a natural question here, what about L'Hopital's rule applied to this form? And
I tried that.
Yeah, so maybe I might leave that as an open question. What happens when you try to apply L'Hopital's rule to this? And then you'll see why Laure did it the way she did. Because you can use L'Hopital's rule.
Oh, you can.
You can try.
You can
always try.
Yes. It's a little bit like integration by part. You can always do it, but if the integral you get is worse than the one you started with, you wasted your time. And in that case, you end up with a limit worse than the initial one, so you wasted your time.
So I'll leave that, give that a go and just see, oh, it is worse. I had to do it the other way.
Because I agree that maybe the natural change of variable would be y equal to minus 1 on x, because you see this up there.
Okay.
And then you run into the same problem, where when you differentiate, there are 1 on x squares which appear. So there are really plenty of things you could do. But this one works really well.
Okay. Right, good. Well, that's the end of the live stream. I hope you found it helpful. Any last minute advice?
Well, please, remember that there are some consultation this week and really until the last exam. Consultations are useful if you've really scratched your head over the problem. If when it says that you actually want to check the assumption, maybe you try to find a similar problem, because at that point you really, really want to know and you're ready to learn something from it. Otherwise, just like, you're watching a movie and in the end you still can't do it. Mm-hmm. And maybe you're confused because it looks like something, but then we don't do this other method. So try to dig, why didn't we do this, just like in that case? And then you try, because it doesn't work, basically. And sometimes if you can't solve the question, maybe it's mathematically correct, but it leads nowhere. Or maybe we didn't do it because it's not mathematically correct. So you need to know. So if you get to a point where, after trying hard, you still don't know, it's a good time to come to us.
Yes.
And the forum will still be working.
Yes, you'll definitely find me on the forum. I am traveling a little bit, but I will always be checking the forum.
Okay.
All right, so I guess we'll stop there and I'll hit end stream.
So thanks for attending.